Hi, everybody. Welcome back. Today we are going to talk about section 23b, discrete probability distributions. Now, if you remember yesterday, we were talking about discrete random variables and how they can list the different distinct possible outcomes given a particular event. So we're going to continue with that idea today and talk about discrete probability distributions. So we've seen before, right, how we could assign different probabilities to different events and everything. However, whenever we do probabilities, the stuff right here in the blue box has to be true, and it kind of says a lot here, and I'll go through it and I'll sum it up in a little more plain English in a second. But it basically says if I have a random variable x, right, and saying that this random variable x could be any of these values, right, with corresponding probabilities for each of those values, such that the probability of x being a particular x value, that's going to equal a particular probability value, right? So the probability of x equaling x1 is going to be probability 1, and the probability of x equaling x2 is probability 2, etc. And if that happens, then there's a couple of things. We know all the probabilities have to be between 0 and 1, right? And we know that the sum of all the probabilities, which basically means if I add up all the probabilities, what does that mean? It has to be 1. And that set of probabilities is going to be what we call the probability distribution of x. What all that means is basically that if I have a probability distribution, all the probabilities must add up to 1, right? And that makes sense. We've seen that in different charts and graphs and tree diagrams and things where all the probabilities of something occurring have to equal 1. And all of those possible probability values, we call that the probability distribution of x. And that's what we're going to look at. So if you recall, again, remember I mentioned discrete random variables, and that's what we looked at last section. So if you look at the intervals that value might take, like for instance, and here's some different notation. We're going to look at the probability that x equals 3, or the probability that x equals a particular value. But we also might say, what about the probability of it existing in a range of values? What's the probability that is at most 3, or what's the probability that it's between 3 and 7, or the probability that it's that it's at least 3 but less than 7, things like that. So that's where we're going to look at different distributions. Here's an example of that. So let's look at this particular one. We have this idea that a magazine store records the number of magazines purchased by its customers. Some of them, 23%, purchase one magazine, 38% purchase 2, 21% purchase 3, 13% purchase 4, and 5% purchase 5. So that's the event, people buying magazines, right? What is the random variable here? The random variable x, right? What does x represent? X is going to represent not the number of people, right? But it's the number of magazines sold, right? It's the how many magazines are going to be sold. So it's the number of magazines sold, right, to a particular person. So what's going to be the probability that a person buys 1, 2, 3, 4, or 5 magazines, right? So we're looking at the number of magazines purchased by its customers in each week, and that could be, what's the probability of a customer purchasing 1 or purchasing 4, things like that. So if we made a probability table, it would look something like this. We'd say, what's my value of x? Well, x could be 1, 2, 3, 4, or 5, right? And then what's the probability of x equaling x, that value? Well, the probability of x equaling 1 is going to be 0.23, right? We said it's 23%, right? For one magazine, it's going to be 38% or 0.38. For 3 magazines, it's 0.21. For 4 magazines, it's 13%. And to purchase 5 magazines, the probability is 0.05%. or sorry, 5% or 0.05. So can we make a probability distribution using a spike graph? Do you remember what a spike graph is? It's like a bar graph, but they're real thin lines. So again, down here at the bottom, this is my x values, right? 1, 2, 3, 4, or 5. What's the probability? Whoops, if I knew how to write my numbers right. What's the probability that x could be 1, 2, 3, 4, or 5? Well, I'm just going to do a random range here, 0.1, 0.2, 0.3, 0.4, 0.5. I guess we don't need to go that high. So 1 is going to be 0.23, so that's going to be a line up to about here. Let's do it in a different color just to make it nice. 0.23 is about right there. 0.38 is about right there, almost to 4. 0.21 is right around there. 0.13 right around there, and then 0.05 right around there. So my spike graph is kind of going to look like that. And I think I have a good picture of it down here. Yeah, there's a little bit nicer than mine. And they drew their table horizontally, but you get the idea. So that is the number of magazines that are recorded or that are purchased. And that's what a random variable is going to be. And what are the probability of each of those numbers occurring, right? And that is our probability distribution of x, all of these numbers. What can you tell me about all of these numbers here? Then I add them all up, they equal 1. That's a probability distribution. Good? Let's continue on. How about another example? So now that we know what a probability distribution is, I want to focus on, and I just wrote it right into the example here, but something called a probability distribution function. And that's the key term here. What is a probability distribution function? Probability distribution function is a function that when I plug in each of my values for x, I get probabilities that equal 1. When I add them all up, I'm going to get a probability distribution. So if we wanted to show that these are probability distribution functions, what does that mean? So for this first one, that means if I plug in 1 for, if I plug in 1 for x, and then I plug in 2, and then I plug in 3, and then I plug in 4, I'm going to get 4 different values, right? If this is a probability distribution function, then all 4 of those probabilities, right? So for letter A, the probability of 1, the probability plus the probability of 2, plus the probability of 3, plus the probability of 4, they should all equal 1 when I add them all up, right? Same thing with letter B. By the way, what is this? Remember this? That 3 choose X? Well, that's going to be, if we had N choose R, right? That's going to be N factorial over R factorial times N minus R factorial. That was when we did the binomial coefficient. That was a little while ago. But I'm not going to have you work these out. I'm just going to show you the answers because I'm assuming you can plug your numbers in. So can we plug those numbers in? Can we plug each value of x into this first one and into the second one? So into the first one, as I mentioned, what's the probability of 1, 2, 3, and 4? And if I plug in 1, 2, 3, and 4 into this equation right here, I get these 4 numbers. I get, as it says, I get 2 34ths, 5 34ths, 10 34ths, and 17 34ths. When I add them all together, what do I get? I get 1. So because I get 1 when I add them all up, that means that this is a probability distribution function. They didn't equal 1 when I added them up, then it's not a probability distribution function. It's just some other regular function. But in this case, it is a probability distribution function. Likewise, if I choose when I do this one, p equals 0, p equals 1, p equals 2, and p equals 3, and I plug those all in, I get these numbers, and lo and behold, look at that, we add them all up, it equals 1. So this is also a probability distribution function. Good? Fantastic. Let's go on, try one more problem here. It says, a bag contains 4 red and 2 blue marbles. 2 marbles are randomly selected without replacement. If x, that's my discrete random variable. If x is going to denote the number of reds selected, well, let's find the probability distribution of x, meaning the probability of how many reds could be selected, right? Well, there could be because there are 4 red and 2 blue marbles, and I'm selecting 2 marbles. So I could have no reds, I could have 1 red, or I could have 2 reds, right? I can't have more than 2, I'm only selecting 2. How would I figure this out? Well, I need the probabilities, right? So I need the probability of each. So let's draw a tree diagram. That's a pretty easy way of doing it, right? So if I start here, remember the tree diagram, and if I select a red and then I select a blue, what's the probability of me selecting a red first? Well, there's 6 marbles, so red would be 4 out of 6, and blue would be 2 out of 6, right? And remember, this is without replacement, right? So what is the rest of the tree diagram going to look like? So now what's going to be the probability of me selecting a red or selecting a blue? So for me, if I've already selected a red, that means there's 5 marbles left, right? And 3 of them are red, so that's going to be 3 out of 5. And blue is going to be 2 out of 5, right? And then if I selected a blue first, what's the probability of me selecting a red or a blue? Well, if I selected a blue first, it means all 4 reds are there, so it's going to be 4 out of the 5 remaining. And if I've already selected one of the blue, then the odds of me getting the other blue is 1 out of 5. And what do I do to get my final probabilities of each of these outcomes? We multiply the probabilities together, right? So 4/6 times 3/5, and 4/6 times 2/5, and 2/6 times 4/5, and 2/6 times 1/5, right? All the way down. So let's start with this one. So 4/6 times 3/5, that's going to be 12 over 30, right? And then what's the probability? The next one is going to be 8 over 30. And the next one is also going to be 8 over 30. And the last one is going to be 2 out of 30, right? And again, when I multiply each of those branches together. Now, my first question is, do these all equal 1? So if I add them all up, add up all these fractions, it looks like it's going to be 30 out of 30, which is equal to 1. Phew, that's good, because that means it is a probability distribution. But now, what are my probabilities? I'm not going to list all 4 of them, because remember, I have to go by my discrete random variable, which is, as it says up here, the number of reds selected. Those are my probabilities. Well, which one is it where I have 2 reds selected? That's going to be this one, x equals 2. That's going to be that probability, which is 12 out of 30, right? And then what's the probability of 1 red being selected? Well, isn't that these 2 together? So that's going to be where x equals 1 red selected. That's going to be 16 out of 30, right? And then what's the probability right here? This is going to be, if I don't select any reds, I got 2 blues, that's going to be 2 out of 30. And right up here, 12 out of 30. So these are my actual probability distributions. It's not the original 4, even though I know they're still going to add up to 1, because those 2 in the middle are both part of my x equals 1 red, right? So now so what is my probability distribution? It's these 3 values right here, right? That's when x equals 2, 1, or 0. And can I illustrate using a spike graph? Well, they did it down here. They can draw it better than I can, so I'm going to do this. So if you'll notice, here is my, again, same probabilities, 2 out of 30, 16 out of 30, 12 out of 30, which is what I had up here. And then here's my spike graph, right? So probability of me not getting red at all, pretty low, 2 out of 30. Of me getting 1 red, 16 out of 30. And then of me getting 2 reds, that's actually going to be 12 out of 30. And there we go. Make sense? All right, fantastic. So notice how we, again, used what we were looking for, which was the x values, my discrete random variable, and looked at the outcomes that I was looking for in this particular case, which was how many reds could I get? And my outcomes were 0, 1, or 2. And I looked at the probability of those outcomes. So it wasn't the probability of every single event, it was the probability of the outcomes that I was looking for, which was the number of reds selected. And that is our the idea of a probability distribution for my value of x, my discrete random variable. So here is an assignment that I'd like you to do. It is from section 23B. Just a few problems. It's really only 4 problems, and there's a couple parts mentioned for each one. And that coupled with 23A, that's your assignment for the week. And that's it. So both of these assignments are going to be due on Monday, which is, I believe, April 6th. Let me check real quick. Monday is April 6th. Yeah, so you have 1 week to do them. I expect you to have them uploaded into eCampus by April 6th. And that's what we're going to get credit for. Also, don't forget this week to please check in with me on the discussion boards. I'm just going to have you kind of touch base, make sure that you're able to watch the videos and get the assignments. Later on, the discussion videos might be something else related to math or IB or college or something like that. But for right now, just going to have you check in on there. So again, check out the modules, check out the assignment. Make sure you can upload them both into eCampus by Monday the 6th. If you have any troubles or problems, please leave me a message on the discussion board or drop me an email. Talk to you soon, folks.